All right, let's look at what universal gravitation is. Now, so G, or gravity, it's 9.81, right? I mean, that's what it is, an acceleration. Sure, we can calculate or measure that, but where does it come from? Why does Earth have an acceleration? Now, most of you probably know the story of Newton and the apple, right? But my guess is it's a little bit incomplete. Newton basically discovered gravity, right? I think a more accurate statement would be that he questioned how gravity worked. Now, the idea of an apple falling, is not a difficult stretch of the imagination, I hope, right? It makes sense. It's going to fall. It's what we expect. But let's think a little deeper. Why does the apple fall to the earth and not the earth rise to the apple? Now, let's get some distance between our apple and earth. Same apple, same earth. Apple still falls to the earth. Makes sense? Sure. Brain still intact. What about now? What if we have a really small earth and a really large apple? What falls to what? Or what rises to what? Now let's jump back. Where does gravity come from? A lot of you might have said in your head, it's because Earth has a mass. Sure, that's part of it. But if that's the case, what happens when the apple was bigger? What happens when the apple has a mass greater than the Earth? Is gravity still because of the Earth? Is gravity now weaker? Now you maybe want to change your mind and say, well, now gravity is because of the apple's mass, not the Earth's mass. Newton understood this. Newton knew that gravity was a property of attraction. Now, attraction requires a minimum of two masses. So Newton felt that gravity was not just the property of one mass, but of both. So the apple falls to the earth, but the earth falls to the apple as well. This is the third law again, right? The earth's movement is just infinitesimally small compared to the apple's movement. Think back to the horse, cart, and earth question. Now, Newton wondered about this force of attraction. He wondered about it extending all around us and into the heavens. Now we can imagine that, right? Now we can imagine that force extending all around us, left and right, like fence posts pointing down towards the ground. And we can imagine this extending up into the heavens, into the sky, into the infinity and beyond. So that now when we look at this, anywhere we move the apple, you can see how the force would be the same. The lines are the same everywhere we look. But now, is this really the case? When we expand out and look again, the earth is not flat. The earth is round. What happens when we imagine those lines now on that curved earth surface? Well, our lines are curved. Our lines extend outwards like different radiuses extending off into space. Now, if we look at different areas, we can see how the lines are closer together, closer to the earth, and further apart. Now, this other part is what Newton thought of when he thought of the idea of field strength, that these lines represent the strength of the Earth's gravitational field. The further away they are, the weaker the gravity. The closer they are, the stronger the gravity. Now, you'll need to remember this for Physics 30. Newton realized that distance was also important in gravity. Or perhaps a better term rather than distance is from the center of one mass to the center of the other. Now, unfortunately, in the equations, they still use the term r. And so this r is not radius, but this is from center of one mass to center of the other. Maybe because they're thinking of a line that extends radially outward from the center of one object to radially inwards to the other center of the other object. Regardless of how you interpret it, the r stands for center of one mass to the center of the other. Now, Newton devised that the force of gravity depends on the mass of both objects and the distance they're apart. Force of gravity gets stronger as the mass increases. More mass, heavier masses, stronger gravity. He also knew that the force of gravity gets weaker as the distance increases. Move further away from those objects, the force of gravity gets weaker. Throwing this into equation, we see the relationship of m1 and m2 on top, r on the bottom. This means the masses are directly proportional to the force of gravity, and that the distance from center to center is inversely proportional. So as again, it gets larger, the force of gravity gets smaller. Now, sadly, for all his success, he couldn't solve for this gravity, this big G, what we call the universal gravity or gravitational constant. It just couldn't do it. He was just missing one thing. Anyone got the mass for this? Newton didn't have it. And in fact, it took many, many years before someone was able to devise an experiment to actually calculate the mass of the Earth. So a fellow by the name of Cavendish, which you'll have to read more about to discover. So that's it. That's universal gravitation as fast as I can teach it. There's more information in the notes, and if you read through it more carefully, you'll get a better description than what I did. But if my time is right, I got through this in about 5 minutes. Good luck, and I hope you understand universal gravitation.